let me put up on the screen what we are covering today. So in Buzz, which the front page of our Google Classroom has our Buzz link at the bottom down there. But if we go to our third hour algebra, right here we are. Okay, let's go to our grade screen to see what is due this week. So when I click on the grade icon, it says September 3rd, we have 1.01, solving systems of equation algebraically, and 1.02, solving systems of equation graphically. So basically systems of equation this week. So we're going to learn how to solve them algebraically and graphically. So let's go check out those two lessons today. Hopefully this is not the first time you've seen this, but it may be for at least quite a while. All right. So solving systems of equations. So what do we mean systems of equations? That means there's more than one equation involved. So let's look at this. Here's a little opening picture. It says Danielle's playing the newest app on her phone, Algebra City Defense. Ooh, I wonder if I can download that. In the game, she must help the Mathonauts defend the city against the giant three-headed monster. She can use missiles or ray guns, but she's only got room for 7 of them and only 23 batteries to run them. What will she do? How can she help the Mathonauts save the city? Okay, well, that would be a system of equations to kind of figure out the best combination of ray guns and missiles. So after completing this lesson, you should be able to answer the following questions. What methods can be used to solve a system of equations? And what type of solutions do the methods find? So let's look at systems of equations. So the remedy for Danielle's situation is to use a system of equations. That's 2 or more equations used as constraints or parameters for some situation. For example, after doing more research in the game, she finds missiles use 5 batteries and ray guns use 3 batteries. So she can set up these equations right here. M represents missiles, R is ray guns, and she can have 7 total. So M plus R equals 7. So any combinations of missiles and ray guns. And 5 batteries for each missile and 3 for each ray gun gives her this equation, 5M plus 3R, and she has 23 total batteries. So she's trying to find the optimum number, right? If she just uses 4 missiles, they'll use 20 batteries, and 1 ray gun, that'll use all 23 batteries, but that leaves her 2 empty spots. So there's got to be a better combination somehow. So 2 variables, 2 equations. M and R are in both equations. So how many equations do you predict to be necessary for a system with 3 variables? Yeah, 3 variables, you need 3 equations. So there are 3 standard methods: elimination, substitution, and graphing. So let's see which one you like the best. So here's the first example, solving a system equation using eliminations. And we're going to use as an example, x plus y equals 9 and x minus y equals 3. And it should be 1 value for x and 1 value for y that would make both of these equations true. So first, you want to identify, let's use an elimination. Do you see any opposite coefficients? In other words, is 1 positive and is 1 negative? That would mean opposite coefficients. And in this case, we have that with y. We have a plus y and a minus y. Now, there may be situations where you don't have it, and then we can create opposites by multiplying one equation by -1, and that would change the signs of all of them. But we don't have to do that on this first one because we have a plus y and a minus y. And they're the same number. They're 1y, plus 1y, minus 1y. So all we have to do is just add the equations together. So if we add those together, x plus y equals 9 and x minus y equals 3. X plus x is 2x. Y plus a minus y is 0y. Y goes away, equals 12. Right? So 2x equals 12. Well, now we just solved that. If 2x equals 12, we divide both sides by 2. X equals 6. So we know in this equation, for both of these equations, x would equal 6. But that doesn't tell us what y equals. But if we know x equals 6, all we have to do is substitute 6 back into either equation, either one, and solve it for y. So if we chose the first equation, it'd be 6 plus y equals 9. Subtract 6 from each side, y would equal 3, right? Because 6 plus 3 equals 9. So the answer is x equals 6, y equals 3. If we decide to do the second equation instead, x minus y equals 3. Okay, 6 minus y equals 3, because we know x equals 6. Subtract 6 from both sides. Negative y equals negative 3. So if negative y equals negative 3, we have to divide both sides by negative 1, and y equals 3. So we get the same answer, doesn't matter which equation we use. Just, depending on which one you like better, you can use the first or second equation. You should get the same answer. Now we can check that by substituting 6 and 3 in for both the x and y. 6 plus 3 equals 9. 6 minus 3 equals 3. It works. Now, when we graph it, here's what's really cool. If we graph these two equations, we go to Desmos, we type in x plus y equals 9, and then underneath that, we type x minus y equals 3. Here's what the graph looks like. I'm going to make it bigger. That point where they cross is the point 6, 3, where the x equals 6, the y equals 3. That is the solution of that system equation. That's where those two equations are equal to each other. When x equals 6, both of those equations equal 3. So when you graph it, all you have to do is find the common point, and that is the solution for that system. All the other points are not equal to each other, but that point is the same on both equations. All right, let me go ahead and make that smaller again. All right, back to 100%. If you want to learn more, there's another box on systems of equations that will give you more information. It gives you another one to try. They can give you another example. So if you didn't understand that one, look at this other one and see another example on how to do that. All right, so I'm going to close that. I'll leave that for you. We're not going to cover every single thing in here because you have access to this. You need to go back and check that out. Otherwise, we'll be here all day. All right, let's look at real world applications of this. The big promotion. So you've been working the box office at a movie theater for a year now, and you're anxious for a promotion. So your supervisor asked you to find out how many adults and how many children attended the recent screening of Amazing Algebra II. The first one was so good, they had to make a sequel, obviously. The total number of adult and child tickets sold was 150. So 150 people bought tickets to the movie. Every adult ticket was $9, and a child ticket was $6. And the movie theater made $1,155. So the supervisor says, okay, how many of those tickets were adults? How many of those tickets were children? We sold 150 of them. We made $1,155 in money. Well, to figure that out, you can either do a lot of guessing, or that's perfect for a systems of equation. So let's work through this. Looks like you need some algebra to solve this. So we counted the number of adult tickets and number of children tickets, A and C. We'll call them A and C. And the total sold is 150. So what do you think our first equation would look like if we know that we have adult tickets and children tickets, A and C, and there's 150? Any guesses? I'll let you put in the chat if you want to think. That -7 is wrong. We're looking for an equation, so we need an equal sign in it. Oh, Rachel's got it. The adult tickets plus the children's tickets, A plus C, equals 150 because there was 150 tickets sold. Let's submit that. Correct. It gave us an awesome. Okay, so now the second equation needs to be written. Adult tickets are $9. So the total earned from the number of adult tickets sold is represented by the term 9A. So we're going to put a 9 in front of the A. Child tickets cost $6. So that would be 6C. And the total earned was $1,155. So if we add, I'm going to put this 9 times A, $9 for every adult ticket, plus $6 for every child ticket, and it equaled $1,155. Awesome, correct. Those two equations together should tell us the answer. So let's look. Identify opposite coefficients. There are no opposites. They're all positive. And we got an A and a 9A, and we have a C and a 6C. So we have a choice. We can either eliminate the A or the C because we need to eliminate one or the other. So if we eliminated the A, we would multiply the first equation by -9. So A plus C equals 150 becomes -9A minus 9C equals -1350. And then the second equation would be a positive 9A plus 6C equals 1155. We didn't change the second one. So now we have opposites with the A. If we decided to do the C instead, then we multiply the first one by -6. So that way we'd have a -6C in the first equation and a positive 6C in the second one. So we need opposite variables somehow. Okay, so now we would just add them together. So if we chose A, we'd add that together. There's the ones we ended up with right there. Oops. So when we add those together, the A goes away. We end up with -3C's because we have -9C's right there and positive 6C's. So -3C's equals -195. So when we simplify that, that's what that equals. If we did the C instead, the C goes away because we have -6C and positive 6C. So we got 3A equals 255 when we add -900 to 1155. So depending on which variable you decided to eliminate, you'd either end up with -3C equals -195 or 3A equals 255. Okay, let's go to the next step, starting with those two equations. All right, and it shows all the work from before. But if we have -3C equals -195 and divide both sides by -3, 65, C equals 65. So we know 65 child tickets were sold. If we went the other direction and eliminated child tickets with the 3A equals 255, we know 85 adult tickets were sold because we divide both sides by 3. So now we can substitute those in there. You can pick either equation to check it. A plus C equals 150. So when we substitute it in down here to check what the other one is, if we did this one, we had C was 65, so we substitute 65 in, and we know that A was 85. On the other one, we would substitute 85 in for A and figure out C was 65. But either way, we would end up with the adult tickets being 85 and 65 being the child ticket sold. So you give those numbers to your supervisor, and you got a promotion because she knows, all right, you know what's going on. So here's some more real world applications. If you want some more examples to go through, candy and cupcakes, how much they cost, all of that. And so you can work through this example on your own time, put this in your notes or something because you can use it on test, but it does let you check your answer here. So for writing the equations and then the solutions. So it does allow you to practice to see if you understand. Okay, that is the elimination method. Now, sometimes when you solve a system equation, the variables disappear. I mean, both of them. You'll add them together and suddenly all you have left is numbers. Well, we'll see there's some special circumstances that happen, and it tells us a lot in that case. So here's a review example. If you want to look at another one, step 1. All right, step 2, step 3. It's got the steps. I'm not going to do all the examples here because I want you to be able to go back and have some time to do this, to go through all these. And again, I don't want to take all day going through because there's a lot of examples here. A lot of good stuff. More examples right here. Create opposite coefficients. Example, example, example. And this will allow you to check, are you doing it right? When you click those boxes, it'll give you what answers you're supposed to come up with. So that's the good thing about this curriculum is as you go through these lessons, have your pencil and paper there. And when it gives you a sample problem, write it down and see if you can solve it because you can check it right here. You can see if you're doing the right steps, if you're getting the right answers. That helps know, am I understanding what I'm doing? If you're doing it totally wrong, then we need to back up and say, okay, what are you missing? Okay, so I'll give you some more examples of that. Literal equations. All right, so when solving equations by substitution, so this is the other method, we looked at elimination, where we either eliminate the first variable or the second variable. This one, we're going to talk about substitutions. So to solve a literal equation for a particular variable, use order of operations to isolate the variable. So in other words, if we have 3x plus 3y equals 9, and we want to use it as substitution, we need to get the x by itself or the y by itself, either way. So in this case, we take 3x plus 3y, we subtract 3y from both sides, then we divide everything by 3, and it ends up with x equals negative y plus 3. So here's some examples to see if we can do that. If we have x plus y equals 1, how can we rearrange that to be x equals? What would that be? If it's x plus y equals 1, and we want to rearrange it to where the x is by itself, we would subtract y from both sides, right? So it'd be negative y plus 1. Or it could be 1 minus y, and it may want us to do that way. I don't know if it's going to count that right or not. If we have x plus 7y equals negative 4, then the x equals negative 7y minus 4, because we just subtract the 7y from both sides, and that moves it to the other side and gets the x by itself. On this one, 2x, here, let me write this one down so we just make sure we know what we're doing here. If I want to, in substitution, I need an x equals. So if I have this problem, 2x minus 6y equals 4, and I want it to be x equals, I need to get everything away from the x and make it x equals. So if I add 6y, it means I still have 2x on this side, but these canceled out. On the other side, I've got 6y and 4, 6y plus 4. That's not 10y, because that's just a 4. It's not 4y. I can't combine those. 6y and 4 are separate terms. I don't want 2x, I want x. So let me divide both sides by 2. So this is x equals 6y divided by 2 is 3y. 4 divided by 2 is 2. So x equals 3y plus 2. Just by isolating it down to x. So let's put that in there. 3y plus 2. Here's another one that we do the same thing where it's supposed to be x equals. We'd have to move the 15y over. So it'd be negative 15y minus 10, but it was 5y. So we divide it by 5. See that? And this next one, if we had 2x equals negative 6y plus 10, and we divide both sides by 2, all of these numbers are cut in half. Let's see if we're right. No, it filled in the correct answers for us. Oh, it didn't want the x equals. It just wanted us to put it. Solve for x. I put x equals in front of all that, so it counted me all wrong. But that's the answers we had, just without the x equals. So look at what it says is the correct answer and know, okay, we had it correctly. That's it. If it has something totally different, then we messed it up. All right. Here's some videos on how to solve through substitution. Here's one video right here. It's 2 minutes and 48 seconds. I'm going to work this on paper rather than having you watch the video, because that video you can go back and see anytime. All right, let's put this up on our screen. Okay, so here is the problem they had right there for us to work. All right. So looking at these two equations, the easiest thing to isolate would be the y, because this is the 3y, 4x, but there's a y. We can rearrange that equation. 5x plus y equals 9. Subtract 5x, because we can pick any one of these to isolate. Since that's by itself already, that's the easiest one. So y equals negative 5x plus 9. All right, so we're taking this first equation and we're changing it to this, because we can make it a y equals. So since this is what y equals, we will take this and substitute it in for y. All right, whatever this is will be substituted in for y, because that's what y equals. So now 4x plus 3, not 3 times y, 3 times what y equals. 3 times negative 5x plus 9 equals 16. Okay, this is exactly the same equation as this, except we've taken the y and substituted what y equals. Y equals negative 5x plus 9. So let's simplify this now. It means first we need to get rid of the parentheses. 4x plus, 3 times negative 5x. That's going to be a minus. So we'll subtract the plus. Minus 15x, right? Because 3 times negative 5. And then 3 times 9 plus 27 equals 16. 4x minus 15x. That's minus 11x. And we need to subtract 27 from both sides because it's not an x. All right, so when we do that, we got negative 11 over here. So negative 11x equals negative 11. We got rid of this from this side to leave just that. So divide by negative 11, x equals 1. Okay, so now we know x equals 1 in this system of equations. We can now take this x and go back and substitute it in. Y equals negative 5 times 1 plus 9. Well, negative 5 times 1 is just negative 5. So y equals 4. So our solution is the point 1, 4. If we graph both of those equations, in fact, let's do that. And the first equation was 5x. And we can go back to the original equation. I can do it either way. I can take y equals negative 5x plus 9 or 5x plus y equals 9. But this is the equation originally as it was in the problem. The second equation was 4x plus 3y equals 16. Look, there is the point 1, 4. That is the solution for both equations. It's the same point on both lines. That's the only place where those lines cross. The only place where those points are equal to each other. So when we go back and we look at our solution, we said 1, 4 was the solution. We can test that. 5 times 1 plus 4 equals 9. That's taking the original equation and substituting 1 in for x and 4 in for y. 1 and 4. 5 plus 4 does equal 9. That's correct. And then 4 times 1 plus 3 times 4 equals 16. So this is substituting in 1 for x and 4 for y. So this is 4 plus 12 equals 16. That checks out too. So checking our solution shows it's correct, and double checking it by graphing also gives us the answer. So that video will show you all of that too. Yes, I'm going to do all that. But anyway, it'll get down to where it has 1, 4 on there somewhere. It'll detail all that for you. Here's another example using substitution with another problem. I'll let you watch that. And there's 3 other ways this problem could have been solved. You could isolate the y. See, they did it by isolating the x right there. You also could isolate the y, the x, y. Like I said, we had choices. When we did this, we could have isolated any one of those 4. But since this one was just a y, we chose that because that's easier. All we got to do is move the x's and it's by itself. If we chose this one, we'd have to divide everything by 5, or divide it by 4, or divide by 3, and we'd end up working with a fraction. You can work with fractions, but it's just a little trickier. So if you can avoid that, it makes things a little easier in yourself. All right. Here's some others you can work on your paper and check it. Let's go to Daniel with her systems equations. M plus R equals 7, 5m plus 3r. Which do you think is worse, elimination or substitution? Which one would be best? You can do it either way. So it shows you how to do elimination, shows you how to do substitution, and either way you would come up with the same answers. M equals 1, R equals 6, M equals 1, R equals 6. So you can use either one. Just sometimes one equation looks easier than the other to do. In some methods, it really works that way. Let's see what we have here. Okay, system equation with 3 variables through elimination. So here's one with 3 different variables. So you have to identify or create. So in 2 of them, and which ones did they choose? They chose the first one and the second one. The y is already opposite of each other, 2y and negative 2y. So when they add those 2 together, they get just 3x plus z equals 5. But we can't identify one variable yet because that doesn't count for the third equation. So now you got to go with the third equation and use it to eliminate once again. So in the first and third equation, right here, you have a negative z and a positive z. The x's are both positive. So they said, well, if I went to, let's see, how did they do that? They decided to multiply the third equation by 2. Oh, they're using the y's again. They have a positive 2y and a negative 2y because you want to eliminate the same variable you did in the first one. In the first one, we eliminated the y, so we need to eliminate the y in the second one. So if they just multiply the first equation by the second equation by 2, because you've already got 2y, that'll give you a negative 2y. So then it'll simplify down to 5x plus 5z equals 15. So that gives us 2 equations that both used to use x and y. We eliminated the y, so we eliminated one of the equations that way. And now we can do the way we've done it with the other ones with just 2. So when you have 3, you have to eliminate a variable using pick 2 of the equations and then pick 2 equations, making sure one of them is the one you didn't use the first time, and eliminate the same variable both times. And then you can go back to the same steps. Substitute and solve. All right, I want to show you, let's see, here's the lesson summary at the end of this page. This is great for your notes. It lists all the steps, so you can have the steps written down in your notes. You can print this and use this as your notes. You know, get you a 3-ring binder or something. Now, here's one of the things to watch out for. So I'm gonna put another equation up here for us to work. So I'm gonna say x minus y equals 4. Okay, and then I'm going to say 3x minus 9y equals 12. I'll say, okay, we're going to solve this system's equations. Oh, wait, no, this is going to be 3y. I did that wrong. 3x minus 3y. So if I want to do elimination, I need to change the sign of one of these and multiply it by, like, let's take the first one and multiply it by negative 3. And that will give me a negative 3x. And that way I can eliminate it. So I would have negative 3x, negative 3 times negative y would be plus 3y. And negative 3 times that equals 12, negative 12. So now I can add these 2 together because I took this first one and I changed it to that. So when I add this together, negative 3x minus 3x, that's 0. Negative 3y plus 3y is plus 0 equals, all my x's and y's went away. Something weird happened there, right? All we have is 0 equals 0. Why would that be? Well, a hint towards that is let's graph them both. So the first equation I said was x minus y equals 4. Okay, here's what the graph of that looks like. X minus y equals 4. Let me turn that off and graph the second one. 3x minus 3y equals 12. There's the graph of 3x minus 3y equals 12. Now I turn the other one back on, the green one. Well, look, it's the same line. the same line. So every solution is works. When we solve the system's equation and we get like 0 equals 0, or if we got 4 equals 4, or -9 equals -9, anything that's a true statement. This is true, that's true, that's true. That means these are the same line, and every X and every Y will work. If we substitute 5 in for X, so if X was 5, 5 minus Y equals 4, so Y equals 1. So that means that would work. If I chose X equals 0, 0 minus Y equals 4, that means Y would be -4. And that would work also. That means there's an infinite number of things that work. Basically, every X and Y that's here, 0 and -4 works. 1 and -3 works. Every point, -2, 2 and -2 work. All those points, every point you see on that line would work in both equations, and they would be true. There's an infinite number of solutions. So if there's an infinite number of solutions, that means they're the same line, right? Because every point they're crossing everywhere, because that's what we're checking. Where are they crossing? Now there's another case, another special case. Let's say we have X plus Y equals 4, like we had last time. And we have, let me think. Let's say X minus Y equals 4. Is that going to work? No. We try that. -X, -Y. Yeah, let's try this. -X. If we have X, I didn't put it up on your screen. If we have X plus Y equals 4 and -X minus Y equals 4, and we solve that, we've already got a positive and a negative there, right? We have a plus Y and a minus Y. So we can just add these together. X minus X, well, that's 0. Y minus Y, that's 0. And this is 8. We've got 0 equals 8. Well, that's different than 0 equals 0 because this is not true. 0 never equals 8. Well, that's one of those special cases. Let's graph that and see, why is there not a solution? Why did my variables go away and all I've got something that's not true? So if we say X plus Y equals 4 is that line. And the other one was -X minus Y equals 4. Oh, that's why there's no solution. When we graph it, look, they're parallel lines. They'll never touch each other. We zoom out now, they never touch each other. They're parallel lines. So there is no solution. No solution. Because this ended up with a statement that was not true, no solution. This up here, 0 equals 0, infinite solutions, right? 5, 1 was the solution. 0 and -4 was a solution. 4, 0 was a solution. There's an infinite number of solutions when 0 equals 0 or 4 equals 4 or anything that's true. No solution if you get something that's not true. And again, you can see all that by graphing it. So that is that special thing. When both variables are eliminated, right here, in our lesson summary, if you're left with a true equation, like 0 equals 0, that means there are infinitely many solutions. And it's the same line. If you get a false solution, 0 equals 8, that means there's no solution and they're parallel lines. All right, so that's the steps for elimination. Here's the steps to solve substitution. So these are great for your notes. So you get to an assignment, a quiz, a test, anything. It's great to have these steps in your notes, so exactly how you do that. And maybe an example or two written down so you know what those steps mean. And then here's the steps for 3 variables using elimination and the steps for 3 variables using substitution. All right. There we go. There's the lesson summary. The rest of this lesson you'll see is example problems, practice problems for you. All right, solve each system equation and match it with its solution. So here's 5 practice problems for you. And when you come up with a solution, you click it and then you click, let's say you solved it and it was -1, 2. It's probably not. Oh, it was. See, when you click it, you click the solution and the answer. If it's correct, it'll go away. Here's some different ones down here. 3 problems for you to practice down here. And it will tell you if you're correct or not. It'll tell you if you're correct. More practice problems on page 8. Solve this distance equation and select check my work. See if you're right. It'll show you how to do it. So this is for you to practice on paper. And here's where you can check to see if you did it correctly. This says use elimination method. Do that with the elimination method. Check to see if you did it correctly. And there's 6 problems there. You can go next. So there's lots and lots of practice. Lots of opportunities for you to learn how to do it. If that was confusing or you still don't think you got it, no, we just looked at it briefly. You need to practice it to really understand it. Master the skill of solving systems of equations through substitution. All right, solve the following using the substitution method. Which answer is it? With this right here, is it y equals -4, z equals -5, or is it +4 and -5? Solve that and figure out which one it is. And it gives you 10 different practice problems right there. Once you answer this one and submit, then you go to number 2. Lots of practice problems. Oh, here you just drag this to its solution. Oh, here's the solution. You work this and say, okay, well, I think this one's -7.3. So I drag it there. Oh, that's not right. It won't let me. So I go back and look at my work and see what I messed up. Say, oh, I did something wrong. Maybe the answer was over here. Oh, look at that. That one had no solution. So, but this gives you a chance to work that and see what you got. Then after you get through these practice and you feel good with it, then you can go to the solving equations algebraically assignment. And you see you got 3 attempts. So if you bomb it the first time, you still have 2 more attempts to go back and see what you missed and figure out what you were doing wrong. 1, 2, 3, 4, 5 multiple choice problems. Gives you a system equation. You give the answer. System equation. You give the answer. And see, that one has a fraction answer. Use substitution. Find the answer. This one, they give it to you as a word problem. So you'd have to write the 2 different equations and find the answer. And then here's another one with word problems. And you're supposed to write the 3 equations that fit this word problem. All right, the other lesson we won't spend as long on because we've kind of already looked at it in pieces. Solving it graphically. Well, we've already graphed some, and we kind of know what that looks like. But let's see what the lesson says here. Solving it graphically. This is only 6 pages. If we look at this, here's a video where she's going to show you that, and it is 2.5 minutes. So I'll do that for you. Here's a review on solutions of equations. All right, solving that. Again, I'll let you look at that later in your own time. So this says you can solve this by graphing. To start, graph each one in the same coordinate plane. So let's graph y equals 3x minus 7. Let's see if I can copy and paste that into Desmos. Yep. Y equals 3x minus 7. There's the graph of that one. And the other one says y equals -2x plus 3. What's the solution? The solution is 2, -1, because that's where they cross. That's where they're equal to each other. So I go back here and, oh, they're going to graph it for me there. Graph it there. And they show the solution is 2, -1 right there, just like we did. Check my work. 2, -1. That's what we did on Desmos, 2, -1. Important note, the solution to a system equation is the point on the graph where the two lines intersect. That's where they're equal. Is it possible to have more than one solution? Okay, now they've given us some. Well, they just get you thinking about it there, but they didn't go the whole way. Or no solutions. Well, that's where we looked at. If we had parallel lines, there's no solution. If they're the same line, there's infinite solutions. There it is, infinite solutions. So when they graph that and graph that, they're the same graph. See, so infinite solutions. Finding solutions using technology. Yeah, that's what we're doing with this Desmos calendar. The, graphing calculator, I mean. Check your work. Just graph it. Write the equation, graph it, and we don't have to do the elimination or substitution. Just graph the equations. So write the equations, and then it gives you the answer. Page 4 would be the last page. So one of the great ways to apply substitution when you're faced with an equation like this. Oh, this is the good one to look at. This one, they equal each other. What do we do if they equal each other? All right, let me do this. 5x minus 11 equals -2x plus 3. Okay, so if we have a problem like this, like, okay, how do I do that, Mr. Brock? Well, it's easy. We can just set this equal to y. Y equals 5x minus 11. And if these equal to each other, then we can substitute y in for this, and that would be y equals -2x plus 3. Well, we said these are equal to each other. Then we said they're both equal to y. Well, if they're both equal to y, that means they are equal to each other. So all you have to do is take this and rewrite it, and now you've got a system of equations that you can graph. You can graph both of those and get the answer. So when you have it equal to each other, just set them both equal to y. That's legal, because if we say this is y and we say it's equal to that, then that's also y. They're both y. So y is equal to both of them. And graph that and you get your answer. So I'm glad they put one of these examples on here. All right. Let's see. Find the solution to this equation using graphing. They did this and a table. So put the points on the table. So there's an equation. Points on the table. If you extended that to be a line like that, it would show you where that table and that equation from the graph would match each other. That's the point of intersection. 1, 0 would be the solution to a graph and the points. You just put the points on the graph. Here's another one. Points on the graph. Put the points on there. You see the points will run right next to it. If you extend that, they're parallel. There's no solution. Here's the lesson summary. This one was shorter than the others because this is just putting things on a graph. As long as you understand what it looks like on a graph, here's the important things right here. One solution. If they intersect each other on the graph, that is the solution, that point where they intersect. If they're parallel lines, there's no solution because they're never equal to each other. And if they're the same line, it's an infinite number of solutions because every point that they have on their lines are the same. All right. And equations could be verbal, algebraic, graphing, or on a table. We can handle it either way. Let's look at the assignment on this one real quick. Solving systems graphically. Again, you have 3 attempts. But on this, you can use graphing technology. Put these on Desmos. Put this equation in, put this equation in. Which one of those points do they intersect? All right. Here they give you the graphs. Well, they give you 4 graphs and they're saying which one of the graphs is this one? Y equals -2x plus 3 and 2x plus 4, y equals 8. Well, if you don't know by looking at it, put those on Desmos and see which one of these it looks like. All right. So that is your assignments. I'll leave there. So when you look at there, we're supposed to do 1.01 and 1.02 this week. All right. That's thrown a lot at you to start the year here. Systems of equations. Remember, you can always graph, even if you're solving it by substitution or solving it by elimination, you can always throw it on a graph and double check yourself. Well, I got the answer is 0, 0. Is that right? Well, I don't know. Let's graph the two equations. Do they cross at 0, 0? Hey, they do. You must be correct. So graphing is always a great way to double check yourself with systems of equations. Absolutely. All right. Do we understand what we're supposed to do this week? Are we all clear? Do we have any questions on anything? All right. Well, this Friday is an A. We do 2 A's in a row to start. We had B, now AA. So it's an A. So I will be here Wednesday and Friday. No one's grade is below 70% because this is our first real assignments. So you're not required to be here Wednesday or Friday, but I will come to class. If anybody has questions, you can come to class and say, I'm confused, Mr. Brock. I'm trying to do this and I'm lost. Okay, well, let's look at it. So I'll be here. I probably won't stay like an hour and a half if nobody's here, but I will come and stay a while to see if anybody comes in for help. So optional Wednesday and Friday, but I'll be here if you need me. Have a great week.